Good morning, everyone. Welcome to the lecture. This is the first time we're having this lecture on this lesson: microprocessors, microcontrollers, and embedded systems. Uh, that's a long name. Before getting into the main part of the lectures and going through that, we'll cover some basic details about the course and so on, and then we can get on with the lesson. Um, so, this is just a brief outline of the topic areas that we will be covering. We are aiming to cover this semester. Sometimes we may not go into all of those. We may cover certain different topics depending on how it goes. And In the current setting of online teaching and learning, we may have to have certain different approaches to some of the activities that we may do otherwise. But generally, this is the plan, the lesson plan that we have for the semester. Um, there are some suggested textbooks for reference. So I would you could refer them to get a more detailed understanding of the topics that we are covering. Again, it depends on your access to libraries and so on, but I suppose these would be useful to get a more in-depth understanding of number of concepts that we will cover. And the main thing about course materials and sharing of details about courses, so generally I would share things on share the lecture slides. Actually, the lecture slides from the previous previous batch are already online, all the lecture slides, so you can refer them on the course page there. I still don't have access to the KDU LMS, so as of now, there are no plans on using the KDU LMS until such time when I get access and we are able to share information there. So in the meantime, what I would suggest and what I expect is for you all to join a particular Google Classroom that is created for this course. You may join using this particular class code. So if you take a note of this class code, you can use that and join the Google Classroom. So that would be our main mode of communication. I can share notices, information, announcements, and also that will also be used to share things like any sort of online quizzes that we may have. So over the semester, we may have a number of online quizzes and some assignments that needs to be submitted online as well. So those things can be carried out using the Google Classroom. So I expect everyone to join the Google Classroom. And for those students who have not joined the class today, please someone please share this information. I will also forward the same through your course coordinators. So that's sort of the brief things that I wanted to cover before getting on to the lesson today. Are there any questions or concerns regarding these matters? All right, I actually missed an important part. That is, I guess I didn't introduce myself properly. My name is Nimal Skandakumar, and I'm permanently attached to the University of Sri Jayawardenepura, the Faculty of Technology, as a senior lecturer there. And my background is in engineering. I was an engineer number of years back. I haven't been an engineer since. I've been a teacher for a while now. This is the third year I'm teaching this module at KDU. So the previous two batches also have covered this module and a similar module previous to that. My main sort of areas of teaching and research are in computer networking and computer security, but I also teach some fundamental computing modules, including such modules like this one. So that's just briefly about me, and as I said, you would be able to find or communicate with me through the Google Classroom, and I will also share my other communication like my email and contact number and so on the Google Classroom as well, so you may be able to contact me outside of class through that. So if there are no particular questions on matters shared so far, we will get on with the lesson for the day. So today we will just go through a brief introduction into the course, and from next week onwards we will dive down into more detailed topic areas. So we will today have a more of an overview of a number of topic areas that may be relevant to the things that we will cover in the coming weeks, and also some of the things will be as sort of in the form of a recapping of things that you may have covered in various other modules in the previous semesters. So one of the main things, so we'll start from the sort of broader concept of a system. So when we say a system, we are talking about something that is, so it doesn't have to be the larger concept of system doesn't have to be a technical system or a technological system. It can be anything that is working together, multiple parts working together according to a plan. We would identify that as a system. But from an engineering point of view, in an engineering context, we will again still can identify systems based on the similar sort of a definition. So different parts, different modules, different components working together according to a set rules, set plan, and producing certain outcomes, certain results. So that is essentially what we would identify as a system. So a simpler example to understand a system could be a watch, watch or a clock. So if we take that as a system, it has a purpose. So the purpose of such a system would be displaying the time. So displaying the time is the purpose of the system. And we could identify a number of parts, a number of key parts of such a system. So we can have some, in the case of a watch, it could be like the basic hardware components such as needles, batteries, dials, and all these things. And then we will have a set of rules or set of steps that it should take, the system would follow in terms of its regular functioning. So in this case of a system, case of a watch, the system rules would be how the needles should rotate, what should happen every second, every minute, every hour, and sometimes there may be additional rules regarding if it is displaying dates and so on, then what needs to happen regarding that, so forth. So we will have a number of rules like that. So a purpose will be there, a set of components will be there, and a set of rules will be there to outline what will happen in the system. Another example, again, thinking more household, we can think about, say, a washing machine. Again, here we can have sort of some variety of components here. Again, it has a purpose of washing clothes, but then in terms of parts or components, here we can have a number of different components. We can have some mechanical components, some electrical components, and even some electronics components. So like a mix of components, different types of components can come together in a system as well. So it doesn't mean a system will be, when we talk about a system, particularly in the context of this subject, when we are talking about embedded systems and so on, we will talk about systems that has this variety of things that have like mechanical components, electrical components, electronic components, and so on. So we will not have only one type of a thing. So we will have systems involving a number of disciplines, so to speak. And then, as with any other system, a washing machine will also have a set of rules or set of procedures that it would follow when it is doing certain tasks. So it will have certain procedures, set patterns that it will follow in its regular operation. Then, from the concept of systems, we can start thinking about embedded systems. So, before thinking about embedded systems, let's start with computer systems. So, when we say computer systems, most of you may be connected even to this class from a computer. So, it could be a laptop, it could be a personal computer, it could even be a smart device like a tablet or even a smartphone. That may be what you're using. So all of those things can be considered computers. We could also have computers in the sort of form factor or design of mainframes or servers. So that type of large-scale computers are also there. But beyond these type of computers, the normal type of computers that we identify as computers, where we have a certain way of interacting with these computers, there is a totally different subset of computing devices that are even more common than these devices, or as common as these, or even more common as these regular computing devices. So that is what we are focusing on when we are talking about embedded systems. So these embedded computing systems are computing devices, computing components that are there in many devices. So or many appliances. So these are computing devices. They have computing capabilities. So when we think about computing in a sort of a fundamental way, these devices, these embedded computers, will also do the same thing. Because like when we say a computer, it should be able to take some input, process it, and produce an output. So that is a basic thing that we expect from a computer. So in an embedded computing system, also we expect the same thing to happen. But in a general purpose computing environment, or the typical computers as we previously mentioned, we have a certain way of using them or interacting them. So in the case of, let's say, we take a laptop, for example, regardless of the operating system, largely our way of interacting with that system is similar. Even when we think about other sort of mobile devices like a smartphone or a tablet, you'd still have a similar way of interaction in a broader conceptual way. Whereas comparing that to an embedded system, they will have a significantly different way of interacting with them. So, say for example, an example could be, we may find these embedded systems in a car, maybe on a camera, or even in a washing machine. And say if we take again the example of a washing machine, the computer in a washing machine and the way that we interact with that is totally different from how we would interact with a laptop, how we would interact with a general purpose computer. So that is going to be one of the key differentiations between embedded computing systems and general purpose computing systems. So we would find these in lots and lots of places, and as we go into the age of Internet of Things and so on, we are going to find this even more and more in many devices, even from like toaster ovens and all these things that didn't have embedded computers in them previously are getting such things already. So that is the context we are looking at embedded system from. So as a definition, we can define embedded systems as something that has the computer hardware and some software also embedded as part of it. So say if we take the case of a washing machine, there will be a hardware component, there will be a hardware component of the computing devices in that, and then there will also be some software component that is going to do all the relevant computations related to washing the clothes. So wash cycles, different rinse cycles, and all these various settings that you may find on a washing machine, those things could be controlled by this particular computer. But one of the main difference that we may find in such embedded systems is related to where this software would lie. So if we think about a general purpose computer, what we would have is, in that general purpose computer, we would say you may use an office application like word processing application on your laptop. Then on the same computing device, you may go and use a different application like a web browser or a online meeting software or even a game. So you are using the same computing device for a number of different purposes. But at the same time, if we think about a computing component inside a washing machine, that one is always going to do one thing. It is going to have a software, but that software is going to be in many ways permanent. It is not going to be replaced as frequently as we may do in a general purpose computing environment. So, and in many of these embedded systems, it is commonplace to find these software loaded into what is called a read-only memory, because there is no expectation for these things to be modified or these things to be changed or updated in a regular fashion as in a general purpose computing environment. We may find these software in an embedded system loaded onto a read-only memory, and we may not have a typical storage device as we would have in a general purpose computer, like a hard drive or any other sort of external storage devices may not be necessary in such a embedded system as well. So now can you think about some examples of where you may find such embedded systems? We have already mentioned few examples so far. I have talked about washing machine too much already, and I am planning on talking about washing machines a bit more as well. So maybe other than the washing machines, maybe are there any other examples that you would like to share?
Electrical vehicles?
Yes, definitely. Anything else? You can just, if you want, you can unmute and speak, or even you can use the chat window and send your answers that way as well. In many ways, this would be much more easier in terms of communication in an in-person class environment. So any other systems that you are familiar with? Maybe if you're at home now, maybe look around and see, are there any things that you see that may have what we could identify as an embedded computing system? Okay, so there are many, and I'm pretty sure like at least some of these things are things that you have seen, and some of these things are things that are already around you. Say there may be a TV, there may be washing machines, microwave ovens, refrigerators. Maybe not all the refrigerators, not all these devices are going to have embedded systems. Some may have those. That's the main point as well. Then, as you said, automobiles, cars, or these things, and they may have a number of different components, different aspects of embedded systems in buildings, in elevators and escalators and air conditioning devices, and so on. In agriculture, in space, in medical systems, like in hospitals, various devices in hospitals, various medical devices that are implanted on patients, they may have embedded systems. A lot of office equipment, printers, copiers, and so on. We can some of those can be categorized under embedded computing systems. A lot of engineering tools that you may have used, like oscilloscopes and all these things, they would have some form of embedded computing systems. So the applications of embedded systems, where embedded systems are used, is significantly diverse. So you may find them in many places, and as time progresses, we are going to find them in more and more places. So that is how things are changing. We are in an age of change. It has already started in many ways that we are getting embedded systems, we are getting computing capabilities embedded into many devices that were not traditionally having those features. In some cases, they can be seen as not necessary. Why do we need an embedded system on a toaster oven? But maybe there is a good reason for that as well. So, but the main point is we are finding them in more and more places as time progresses. So say if we take an example of an automobile device, a car, even a motorbike for that example, they will have a number of embedded computing devices. They may have like an overall control computing device, but then they may also have additional localized controllers, localized embedded controllers that are going to do certain different controls, like fuel injectors, brake controllers, and so on. So there will be a lot of sensors, there's a lot of actuators, and so on. So those things would be controlled by such embedded computing devices. So any type of automobile devices, you will find a lot of them. And again, we are finding more and more complex things being carried on by such computing devices with newer vehicles that we get. Even the same is applicable to a lot of motorbikes and that type of devices as well, that type of vehicles as well. So then when we think about embedded systems in general, we can identify a number of key components that would be there in an embedded system. We have already identified that the main things that when we are talking about embedded systems, is this hardware and some embedded software, or the software being embedded onto some form of a read-only memory or some form of a memory that is also available with that hardware. So when we think about the components, so it is going to be the hardware components, and we can have a number of different hardware components as part of that. So an embedded system will have to have a processor, then a number of additional computing hardware. Like conceptually, these are, because an embedded computer is also a computer in many ways, it will have similar set of components. Some processor, some memory, some input-output devices, some various connectivity mechanisms to connect to these input-output devices, and some communication buses and so on, so interconnection and so on. So the basic compute aspect will be similar. The scale would be different and how these things are used would be different, but conceptually it would be similar. Then we would have, beyond the hardware layer, we would have another layer which is the software layer. So in the main application software layer, we would have an application software for that particular embedded system. This is where embedded systems may significantly differ from a general purpose computing system. Even if the architecture or the organization of the computer system is fairly similar to a general purpose computer, the application software and how that is being used would be somewhat different or significantly different in many cases. So we would, in most cases, we would have an application software that is only doing a particular task. Say, if we go back to the example of washing machine, there needs to be an application software, but that application software is only tasked and only things that it can do are relevant to washing clothes. So those are the particular procedures, instructions and so on will be implemented in that particular application software. But in certain embedded computing systems, we may also have an additional operating system layer in the form of a real-time operating system. So real-time operating systems are needed in certain types of systems, certain types of embedded systems. We may need real-time operating system, and the main type of system is a real-time system. So we will have a much detailed discussion about real-time operating systems and how they can be implemented in embedded systems towards the end of this course. But the main thing at this point is real-time systems are a subcategory of systems. You may have already covered that in some other courses possibly, and the main thing to understand about real-time systems is they are going to be having, so say a good example would be a braking system in an automobile, and what we expect is the reaction to a particular command to that system should be executed in a real-time manner. So that is the main significant difference that we would see from a general purpose computing system and a real-time system. And if we build a real-time system as an embedded system, then we would have to use a real-time operating system there. So that is a subset of embedded systems may also use a real-time operating system. So mainly it would be the hardware and the application software would be the main components of the embedded system, but in some cases we may also use a real-time operating system if the underlying system that we are having is a real-time system. So now if we think about, when we think about the embedded system hardware particularly, this particular schematic structure, architecture that you are seeing here, you would see that this is very similar to what you may see in a typical computer architecture. So that's what we meant by the embedded computing system will largely be similar to what you would find in a general purpose computing system. So components like processors, memory, communication ports, various communication ports, interrupt controllers, output devices, input devices. So all these things would be very similar to a general purpose computing device. But what you may also find in certain situations, in certain scenarios, is some additional components, additional hardware components that are more relevant to that particular embedded system. Say for example, if we are building a system relevant in a washing machine, there we may have some additional hardware components such as water level sensors and so on included there. If we are building a vehicle, and if we have a embedded system for the braking system, there we may have a different type of sensor and a number of different other hardware components interfacing with the main computing components. So we would have some standard computing components and the standard input output devices, but then in addition to that we may have some additional hardware components as part of these embedded systems as well. So when we think about the embedded system from a hardware point of view, we may come across certain constraints again when compared to general purpose computing system. So again, if we take the example of many embedded systems, one of the limitations that we will have is these systems may have certain limitations in terms of the space that they can take, the price point they have to meet. So you cannot build a computer that is capable as a general purpose computer, like a laptop, which may cost like $100,000 or 100,000 rupees or something similar to that, and we cannot have such a computer on a device that needs to be sold for a much lesser price point. So then we have to come down in the capabilities of the computer, the main computing components, the hardware, the processors, the memories, and so on will be reduced to match that requirement as well. So what we will end up with is systems that would have, in many situations, will have limited memory. The available memory for processing would be limited. The processor speed itself would be limited. And in many embedded systems, in many embedded applications, particularly the ones that are sort of mobile type applications, or even others that are deployed in certain different scenarios, there may be a limit in terms of the power that they can use as well. Say if it is a mobile device, the power may be limited. If it is a battery powered device, again power may be limited. So those can also be an issue. And one of the other things is, comparing with general purpose computing devices, embedded systems will have certain different expectation in terms of their running time. So in many scenarios, we may say, for example, if it is a embedded system in an escalator or an elevator, that system would be expected to run continuously throughout the life cycle. So unless it is stopped for maintenance purposes, the expectation it continues to work. There's no point in time it will be particularly expected to be shut off. So we will expect sort of different types of life cycle, different types of continuous operation from embedded systems, again when compared to general purpose computing systems. So some of the key criteria that we can use to sort of identify and differentiate embedded systems, again depending on the type of system, depending on the type of equipment that these systems are going into, we would identify different things, presence of different things. So as I said, say real-time operation is one aspect that we can have in some embedded system, but that doesn't mean all the real-time systems are either embedded systems, or the other way around, all embedded systems should be real-time systems. Again, as I said, we will come back to real-time systems in more detail towards the end of the course. Then other than that, like things like say size of the device, as I said, we may have to build it into a small package, so that could be a constraint that we may have. Cost of the device, the time of operation, as I said. Then even things like reliability and safety. Say for example, if something goes wrong on a personal computing device, like a computer or a laptop, personal computer or a laptop, it may be okay and it is sort of accepted and understood that we could restart the computer and things could come back normal. But if we think about the embedded computer on an elevator, the normal expectation is that something will occasionally go wrong, and then we restart the elevator and things would be okay. That is not an accepted way of going about it. Same thing for a braking system in a car. So you can't say I was trying to brake, but the computer was restarting, so I couldn't, the brake didn't work, then I crashed. So that is not a accepted mode of operation for an embedded system. Whereas the same thing may be okay in a general purpose computer. Okay in the sense it is accepted, that is, it would be acceptable to have certain level of failures in certain type of systems, whereas embedded systems, particularly certain types of embedded systems, may have higher levels of expectation in terms of reliability and safety. Then one of the aspects, particularly with a lot of mobile devices, a lot of battery powered devices, we will also have some constraint relevant to energy usage. Say for example, if we are connected to the mains power all the time, it may be okay, not okay, but it may be acceptable to again use any amount of, or at least significantly larger amount of power, whereas the same may not be possible for a device that needs to be powered by batteries for a long period of time. So battery consumption, energy consumption will also have to be a concern there. Then in certain situations, security may be a issue that we have to think about in embedded systems. Given, say, particularly when we are thinking about Internet of Things, smart devices and so on, particularly devices that are also connected to other computing networks, particularly the security of these devices and how the security can be compromised in some of these IoT devices, smart devices, and how people can get through onto other networks. So when considering such scenarios, we will have to think about security as well. So say if everything is perfect, but if the embedded system is hackable, people can break into that system, then that could be a problem as well. So these are some of the things that we will have to think, particularly when we are thinking about embedded systems. That doesn't mean these are not relevant to general purpose computing systems, but these are significantly important and have a particular requirement when we think about different types of embedded systems. So in the examples of embedded systems that we have discussed so far, one of the things that we could have observed is that there are sort of variety of types of embedded systems, and even in the sense of complexity, in the sense of what is expected from them, there are significant differences there. Again, if I think about a washing machine, the expectation is that it is you put some clothes, you select some settings, and it spins and puts water, drains water and so on, and then you get some clean clothes at the end. So that is the complexity of a washing machine. But if we think about a train or a vehicle, there the complexity would be much higher. Or even the case of a camera or a video camera and so on, that may have a significantly different level of complexity and sophistication. So based on these sort of differences that we can observe in these systems, we can classify embedded systems as instead of three, as small scale embedded systems, medium scaled embedded systems, and sophisticated embedded systems. So this classification largely depends on what is expected of the system. It is not the size of these things, it is rather the computational complexity and the various components, interactions that is needed there in that particular embedded system. Based on that, we would be able to classify these embedded systems under these three categories. Say, for example, in the case of small scale embedded systems, things that we can observe here is we will have sort of smaller type of processors, or like an 8-bit or a 16-bit microcontroller, or a processor may be used. There may not be significantly complex hardware would not be there. There may be like maybe few sensors, again outputs going to few actuators or something like that, maybe a display, and some simple software may be present as well. So the complexity would not be higher, and it could be battery operated, and there may be certain limitations of how much power can be used, so that again will dictate what needs to happen in terms of the complexity there, in terms of the power consumption there. And the programming of such software may also be done in a sort of either in some low level or a basic programming language. So an example could be, say, a remote controller, for example, or which could be, we can consider as a small scale embedded system, a remote controller for a television. But when we think about a medium scale embedded system, here we go a bit higher in terms of complexity. We may have certain higher level of microcontrollers or microprocessors, and we may even have additional digital signal processing capabilities, some other sort of RISC computers and so on. The software and hardware complexity may also be higher, and even in terms of programming these devices, we may have to use some advanced level programming. Sometimes if there is a real-time operating system that may be involved, some integrated development environment and so on may be used. Say an example for that could be a television. So the remote control for the television would be a small scale embedded device, but the television itself may be a medium scale embedded system. Then when we think about more sophisticated systems, here now we are thinking about not just single systems, but number of things that are interconnected into say sort of bringing the hardware complexity higher, but also the software complexity becomes higher. And there may be sort of multiple process architectures, or multiple processors, or multiple sort of parallel processing capabilities and so on in certain cases, additional processing hardware, additional hardware capabilities, hardware components interacting with one another. And even from a programming point of view, the complexity would be much higher, and the system would have been designed in certain ways to program it effectively. So an example for that could be, say, if there is a factory, for example, a manufacturing factory, and a number of these things are, number of machinery and so on are controlled by a variety of embedded systems, and those are interacting with one another and so on. So that would be a more sophisticated embedded system. So it largely depends on both the scale of the hardware components, but also the scale of software components in terms of what we expect that hardware to do. So in a smaller scale environment, the processors will be low and everything will be sort of low spec and so on, but also not much complex tasks are expected. But when we go higher, the hardware complexity also grows, but also logical software complexity also grows. Any questions on the things that we have discussed so far? If there are any questions, please feel free to put it as a message on chat, and I'll try to answer them as we go along. So if you want any clarifications, if you want me to explain certain things again, please let me know as well. So now let's go into computer architecture and have a brief recap of what is computer architecture and what are some of the things that we identify by computer architecture. Because as we said, the embedded computer that we are talking about is in itself a computer, and a number of topic areas that we are going to be discussing in this in the upcoming lectures are also relevant to computer architecture. This may be a course that you may have covered in some sense previously. Maybe you have covered parts of it, but this is mainly as a recap of that. So when we say computer architecture, we are talking about, so an example to understand that would be, say, if we say what is a home or what is a house, you can say a house will have rooms, maybe a hall, maybe a dining area, maybe a kitchen, bathroom, car park. So likewise, we will identify certain components or certain parts that are necessary to have a home, so for a house. So that is the basic components that we expect in a house. But when we say the architecture of the house, there we are not only talking about the list of things that needs to be there, but we are also talking about how those list of things are interconnected to one another. So where are the bedrooms, where are the living areas, where are the dining area, kitchen, and so on, and how those things are interconnected, where to where, and so on. So that is the architecture of a house. So similarly, when we talk about computers, when we talk about computer systems, we can think about computer architecture also in the same manner. So one of the two terminologies that we may get to use quite often when we are discussing in this area is computer architecture and computer organization. So in this scenario, when we talk about computer architecture, we are talking about this overall design in terms of what are the instructions for the computer, what are the registers available in the computer, what is the memory addressing scheme. So what are the basic design details of that particular computer is what we would identify using computer architecture. With computer organization, we are mostly talking about the implementation of the said architecture. So here we will talk about the exact specific cache memory that is used, what is the particular hardware that is used, what is the technology that is used to implement those particular architecture details. So those are some of the things that we will talk when we are talking about computer organization. So the architecture will be the design and the computer organization will be the implementation of the same. An example of this could be, say, in Intel Core architecture, the architecture is the underlying instruction set architecture, the underlying design that we would have in the Intel Core architecture, and that would be shared across all the Intel Core series of processors. But if we take a single processor from that family, each of them will have significant differences in terms of their implementation. So that is the difference that we would see in terms of their organization. So they would have different speeds, different internal components, and because of the different cache memories and so on. So because of that, they are going to still have different price points and so on, different capabilities and so on. So what we would have is we would have a common architecture, and in the common architecture we may have different sets of processors, in the same architecture family. So when we talk about such a computer architecture, we can think about it in terms of the basic components of a typical computer. So we can identify some components of a computer as sort of the basic components. So what we can mainly identify is there should be a central processing unit, the central processor, the CPU. Then we should also have some form of a memory. So we should have some memory where information can be stored and retrieved for the purpose of processing. Then we would have to have some form of input-output controllers through which information can come into the computer and go out as outputs. So what we would have is, we would have the CPU where all the processing is going to happen, but for the processing the information needs to come from somewhere, so we will have memory for that purpose. Then after processing and for the information to reach an end user, we should have some input output device, or even for the initial instruction to come through we may have to have some input output device. So those are the three main components that we would identify in a basic computer. But beyond that, we could also identify things like, say, cache memory, for example, that would be there in addition to the main memory, and normally it would be there along with the CPU, so that would be there. Then, say, when we talk about input output controller, then there should be a variety of input output devices. So this could be display devices, storage devices, or variety of computing devices. Computing peripherals can come under the category of input output devices. Then all of these things will have to be interconnected somehow, and we will have to have some form of interconnection mechanism. And one of the most common approaches that we may have is using buses. So we will have some intercommunication mechanism in the form of buses. So we will revisit some of these topic areas again in later part of this course when we are talking about computer interfacing and memory and so on. But this is the general architecture of a computer, any sort of basic computer, and the same one would apply to embedded systems and embedded computing devices as well as general purpose computers also. So now if we think about the central processing unit, particularly the CPU particularly, again there we can identify a number of components, a number of internal components of the central processing unit. So the main component or the core component of the central processing unit, we can identify the ALU or the arithmetic logic unit as the main central component, which is going to do all the computation. So it is going to do all the mathematic and arithmetic and logical calculation. So that main computation is going to happen at the ALU. Then in addition to the ALU, we would also have say some memory locations internal to the CPU, which we would identify as registers. So these are temporary memory locations where data values can be stored before and after the processing happening in ALU. Then we would have to have something that is controlling everything happening inside the CPU. So all the actions that are happening in ALU will have to happen in a particular order, one after the other. So there should be something orchestrating all these activities. So that would be the control unit. Then in addition to this, we would also have another component, the input-output unit, which is going to be responsible for interacting with all the external communication. So what we would have is, we would have the arithmetic logic unit that is going to do all the computations, and it is going to get that information, and the information is again sent, the results will be sent back to registers. Then all these activity will be orchestrated or managed by the control unit, and all the information coming in and out of the processor will be managed by the IO unit. So those are the main components of a central processing unit. Then one of the important things that we will have to see within the central processing unit are the registers, particularly from the point of view of programming and using these computing devices and managing these computing devices from a programmer's point of view. Registers become an important aspect, because registers are the memory locations that are going to be used to store data temporarily before and after processing at ALU. So then that means the type of registers that are available, the amount of registers that are available, will dictate the type of programming that can be done. How many instructions can be executed, how many values can be sent in that instruction, what is the nature of those values will also be dictated by the registers. So some of these registers would be available for directly used by the programmers. So those are any sort of user program can directly access and use these registers to store and read information from. Then there will be some registers that may be used indirectly by the system itself, things such as program counter to keep track of at what level we are in execution of a program, which instruction we are executing. That can be stored in a program counter, which is a special purpose register. Then some registers may also be used by the operating systems for other special purposes. But essentially, registers are going to be some important memory locations when we are thinking about computers from the point of view of programming them. Then the buses are going to be also important, particularly when we are thinking about interconnecting various components of a computer. Buses are going to be the ways how we are going to connect them. So a bus is basically a set of wires that has a particular purpose. So it is just a set of wires, but then it will have a particular purpose as to what it needs to do. For example, if we take a control bus, that is going to carry information relevant to controlling these different components. Whereas address bus will have information relevant to where to read something from or where to write some data onto. And the data bus will carry such data that needs to be carried on. Again, this is something that we will revisit again in much more detail later on, the concept of buses and interconnectivity of components. But the main thing is, in a typical computer, we will have the concept of a bus or a number of buses, and they will be shared by a number of components. So what we may have is the variety of components may connect to the same bus, and all of them may be able to use the same functionality provided by the same bus. So that is what we would have in terms of buses in a typical computer. Then in addition to buses, we may also have to think about the input-output controllers. So as we identified, input-output controllers are the ones that are going to connect to various input-output devices relevant to that computer system. So depending on the type of the computer system, depending on what is happening in the computer system, the type of input-output devices attached to that computing system will also differ. So we may connect some displays, we may connect some storage controllers, we may connect some other input devices like keyboards and mouses and so on. So depending on the type of input-output device we need to connect, we also need some form of input-output controller. So by the nature of that input-output device will require a particular type of input-output controller, and that input-output controller will manage all the communication from that end onwards to the device, and it will directly communicate to the CPU and do the communication on the other side as well. So it will act as an intermediary between the main computing components and the device itself. So it will sit in between, and it will communicate to both ends of the information transfer. And one of the things that we need to remember about input output devices is there can be a number of these in the same computing device. So for example, we may connect to a number of display devices, we may connect to a number of like keyboard or mouse or similar pointer devices, number of storage devices. So we can have a number of different controllers doing different things at the same time, and all of them can be connected through, again, another common bus, and they can communicate with each other and communicate to the main components of the computer as well. Then another concept that we will have to think when we are thinking about the architecture of the computer is about memory hierarchy. So memory hierarchy basically identifies certain observations about the use of memories in computing devices. So even if you take your computer, the computer that you are using, your personal computer that you are using, and think of it in terms of these different types of memories that are available. Say you can attach any amount of removable media, so we'll leave that. Then let's think about the main secondary storage, or the disk that is available for secondary storage. So you may have say number of gigabytes or even a terabyte or more of secondary storage in your computer. But if you think about the RAM or the main memory, that may only be in terms of few gigabytes. So say even if you have 500 GB or 1 TB or 2 TB of secondary storage, or the hard drive, or say solid state drive as a disk storage, you would still have 4 or 8 or 16 or 32, 64, whatever. I mean, like, but still it is going to be significantly less than what you would have as your secondary storage. But then again, if you go a level up, and if you think about the cache memories, again you may have only few megabytes of cache memories in most cases, in most motherboards, in most processors. The cache memory or different levels of cache memory would still be in terms of megabytes. And then registers inside the processors are going to be even less. So what we could observe in this memory hierarchy is, as we go down the hierarchy, the size is going to increase. So size is going to increase down, and we will have only smaller amounts of the type of memories going up. One of the reasons for why that could be is, if we go up the hierarchy, depending on the technologies that are used for those things, and based on what we need to do in terms of that type of technology, the price of these things will increase when we go up the hierarchy. And one of the other things that is more relevant to us from a computing point of view would be the speed of these devices, and the speed will also increase when we go up the hierarchy. So the increase of speed is something that we want. So we want the increase of speed, but because the increase of price is not something that we can readily accept in all conditions, so that is why we would have this hierarchy of variety of types of memories, and then we would use a mix of them, some as temporary memories, some as permanent storage memories, and so on. So that is the main idea about memory hierarchy in the context of computer architecture. Then when we think about the actual computing happening in a computer device, we can think about how the instructions are going to be executed in the processor. So that is the core activity of a computer. So set of instructions being executed to produce results. They are computed and results are produced. So that is the main computing activity happening in a computer. So that main computing activity, we can split that into what is called this instruction cycle. So a number of steps that needs to be taken for such an instruction to be executed. So we can split that into a number of stages, and we can identify them as the fetch cycle. So in the fetch cycle, we will fetch the instruction that needs to be executed next. Then in the decode cycle, we will look into the instruction and identify what are the components, what is the command, what are the values, and what needs to happen about in where it needs to be processed. And then the execute cycle, it will be executed, it will be computed in the ALU, in the computing device, and the results will be processed. So that is the main cycle of execution of instructions. As a sort of a simpler model of this, we can identify a number of stages here. So the first, we will have to go and fetch the instruction from the main memory. So we will have to go and fetch the instruction from the main memory. For an example, we can say an example of such would be, say, add A and B. So what we want to do in this instruction is add two values stored at A and B. So when we fetch this instruction, we can then go into the next stage and identify what are the different values that we need for that particular operation. So here we need to know what is the value for A and B. So then what we will do is we will go and fetch A and B from the relevant memory locations. Once those information are available and stored in the register values as appropriately, then the instruction can be executed and the results can be produced. So that is the basic model of execution, the simple model of execution of instructions. Then in terms of the overall architecture of the computer, we can look at these computing devices in a layered architecture. We can start from the very fundamental level of physical components that are used in building these devices, the silicon devices, silicon components, how those are extracted and so on, the very fundamental level. And then how we build the basic components of transistors and so on. And then how we build the logic hardware in terms of gates and so on. Then how we use that to build the microarchitecture of a microprocessor. And on top of that, we will have what is called the instruction set architecture. That is going to be the interface between the hardware and software layer. Then on top of that, we will have the machine code layer, then assembly language and various programming languages, and we will have the software stack above that. So we can look at this compute architecture in this multiple layers as well. So how things are structured inside a computer is one view, but then we can also identify this layered architecture of overall computing, and we can look at various things in various places. And we will be discussing about number of these layers in the upcoming lectures. So finally, we will briefly also talk about microprocessors and microcontrollers, and we are anyway going to be discussing these topics in much more detail in upcoming lessons, but today as an introduction we will talk about these briefly. So a processor is basically the main heart of the component, heart of the computing operation, and even in an embedded system, that is going to be the one that is the center of the operation. Then, because that is that, anyone who is going to use an embedded system, anyone who needs to design an embedded system, should have proper understanding of such processors, microprocessors and microcontrollers as well. So when we say microprocessors, here we are talking about that main processing element, the CPU, including ALU, program counter, and a number of internal components of the CPU. So that is what we would identify as a microprocessor. So this is the main computing device that is built onto a chipset. So this is the microprocessor that we would normally talk about. But in addition to that, we will have to include a number of other computing components. These memory and input, output, and so on will have to be attached to this microprocessor for us to build a full-fledged computer. Whether it's an embedded system or not, we would still need to build it in the similar architecture. But when we say microcontrollers, these are computing devices that are having everything relevant to that basic computer inside a single chipset, which we would call as a system on a chip. So this would include the microprocessor, but would also include the memory, input, output, and peripherals, connectivity, and so on, will be built into the same device, same chipset. So that is what we would identify as a microcontroller. So particularly in the context of embedded systems, there is a higher prevalence of use of microcontrollers than microprocessors in many applications. It doesn't mean that all of them are going to use microcontrollers and there's no place for microprocessors. And even microcontrollers are going to have processors built into them. So it is the same structure, but the main difference is everything is now inside a single chipset. So there are a number of examples of microcontrollers from different vendors. Again, we will revisit a lot of these in later lectures as well, and we will even study about some of the some particular microcontrollers from specific vendors and study about their internals as well. But one of the main things to differentiate between microprocessor and microcontrollers are, one is microcontrollers are going to have more internal components, more functional blocks built into them. Microprocessor is going to only have a limited number of functional blocks necessary for the microprocessor, and everything else will be connected externally. Whereas in the microcontroller, all of those basic functional components are also going to be part of the same chipset. Then, even in terms of the capabilities of these devices, they may differ significantly. So, because microcontrollers are tightly integrated, all of these things are connected directly to one another inside a chip, there may be certain advantages in terms of computing, communication, and so on, which may be significantly different in a microprocessor-based system. But in the context of application, we would see more microprocessor-based system in general applications and microcontroller-based applications in more specialist applications. So these are sort of some of the main differences that we can identify, and we will talk about each of these microprocessors and microcontrollers in various lectures in the rest of the course. And in the context of embedded systems, we would identify certain microprocessors and microcontrollers as embedded processors. And the reason for that being, they are built for certain applications, they are built for certain embedded applications in mind. So we identified certain criteria such as power usage and so on that is necessary for embedded system. So if some of these microcontrollers or microprocessors are catering to that, we may identify them as embedded processors. Then in addition to these microprocessors and microcontrollers, an embedded system will also have a number of other hardware components such as power sources, clocks, input output devices, digital to analog to digital converters, displays, output devices, keyboards, input devices, and so on. So we would briefly touch upon some of these things as well as relevant throughout the course, but our main focus would be on microprocessors, microcontrollers, and how we can use them in designing embedded systems. So that brings us to the end of discussion for today's lesson. Are there any questions on things that we have discussed so far? So, as always, I always welcome any questions that you may have. So, during the lesson, if you have any questions, you may ask them as well. If not, if you have any other questions, another time you may directly contact me and ask as well. Um, So, as I mentioned at the beginning of the class, please log into this Google Classroom, enroll into this particular Google Classroom. So I will be able to share the lecture slides and everything on the Google Classroom. So already you will be able to share you will be able to join the class, and I will post the lecture slides for today before the end of the day. And if you are interested in all the lecture slides, at least there may be certain changes year to year. I may change slightly, but roughly all the content that will be covered in this course, you can find all the previous lecture slides in this particular web page as well. So that will have the lecture slides from previous year. So if there are no other questions, we may conclude the discussion, the lesson for the day, and we would meet around same time next week. And in the meantime, if you have any questions, you may directly contact me, and please let me know any issues in terms of the delivery of classes and so on. So thank you for joining in this lesson, and see you next time. Bye.